Okay, welcome back to this course on the fundamentals of attosecond science and technology. Today we are in module number 5 of this section on nonlinear optics. So, let us have a look at this module. As always, we have the set of references which I am sharing with you, particularly for this section the book by Boyd is of particular importance, and as always thanks to Professor Trebino for his inputs and materials. Now, in this lecture we will essentially go into these important aspects of the process of harmonic generation, particularly for the low order harmonic generation process, which is second and third harmonic. If we go to third, we will briefly bring about the idea of third harmonic generation, but we want to like sum more difference, that is add or subtract two optical frequencies, right. So, the energy momentum conservation for that, and we will look into so called phase matching. So, as always we are now considering the interaction of light with an atom, and this is an exaggerated cartoon of the same process, where light sets the electron cloud into dipolar oscillations, which we model using the driven damped oscillator model. Here the oscillator is still harmonic. So, if the driver is at a frequency omega, then the displacement x is also at essentially oscillating with the same frequency omega. And we understand that this can lead to three different scenarios, where the frequency of the driver, which is omega, and the frequency of the natural frequency of the system, the eigen frequency of the resonance frequency, can either be equal, in which case they meet at a resonance, and the two oscillations are pi by 2 out of phase minus pi by 2 out of phase, whereas in the other two cases these are either a pi out of phase when the driver frequency is much smaller than the eigen frequency of the oscillator, or when the driver frequency is much greater than the resonant frequency of the oscillator. We essentially have a scenario where the vibrations are between the driver and the driven system are both in phase, right. So, the complex frequency response of the atomic system is captured in this equation, where we have particularly in the denominator, if you see omega naught square minus omega square minus 2 I gamma, gamma being the damping factor. So, when these two are equal, omega naught and omega, we have resonance. We wrote this down in terms of the complex Lorentzian function, and then took the real and imaginary parts of the complex Lorentzian separately out, and we figured then that the real part is an odd function of delta, delta being the detuning between the applied frequency, that is that of the driving electromagnetic field, and the natural frequency of the system, which is omega naught, the atomic system. So, the imaginary part is an even function. We see the imaginary part in green, the real component is shown in violet, and we link this to the refractive index of the medium through Maxwell's equations and the constitutive relations that go along with it, particularly the relation d is equal to epsilon naught E plus P, where P again is essentially unknown until we expand this as a perturbative series in the electric field E. So, it is linear in the field, quadratic, cubic, and so on, but then we must realize that the coefficients of expansion here should be tensorial quantities. This is a second rank, third rank, or a fourth rank tensor. Okay, the J here should be a subscript, please note the typo. But then here we have for a non-magnetic medium the four equations of Maxwell written, taking into consideration the polarization per unit volume, or the polarization field P, right, where it should appropriately fit in the other equation, where this matters, that is dive D is equal to rho free. Rho free was 0. So, we simply have dive E is equal to 0 appearing in this equation. Okay. So, we then realize that we can capture absorptive and refractive phenomena by considering a refractive index as a complex factor, and where the real part is more the refractive index as we know it, and whereas the imaginary part of this complex factor is the absorption coefficient. Then we can write down the entire sort of relation by doing a few substitutions, where E at a point z along the propagation direction is essentially the initial field E naught at z is equal to 0 multiplied by the absorption factor minus alpha by 2 z, and the phase is essentially then exponent of I n the real part of the refractive index times k naught, which is 2 pi by lambda naught the wavelength in vacuum, times z minus omega t. We are considering a one dimensional linearly polarized wave. So, everything is scalar over here, and of course, in a medium we essentially have for the amplitude diminishing by a factor minus alpha by 2 times z. So, all this is well borne out by our current treatment of the way we have written the refractive index. Note that the minus alpha by 2 z and the I times n k naught times z, these two factors which multiply the propagation variable z, can be captured by defining a complex refractive index n tilde, where the real part is n, the usual refractive index, whereas the imaginary part of this is a kappa. Kappa is alpha divided by 2 k naught per definition. We have defined it to be so. If we do that, then we can write down the entire expression, okay, in the form of a neat relation where we replace the real with the complex refractive index n tilde. The tilde is underneath, you could put it wherever you like, but we prefer this for no particular reason in some sense, and but then we write this compact relation which includes both absorptive and refractive phenomena. So, refractive index and both the real and the imaginary part of the refractive index essentially play a role in propagation. Now, a little word on dispersion. So, normal dispersion is when refractive index increases with frequency, whereas anomalous dispersion is when it decreases with increasing frequency, owing to the z shape of the real part of the displacement in terms of the 2 points of the electron cloud, or you can think about this likewise in terms of the polarization vector field, or in terms of the refractive index itself as a function of frequency. This downward slope essentially is the region of anomalous dispersion, whereas the upward is normal dispersion. So, you have small windows of opportunity where some media can have anomalous dispersion, which can help us manage dispersion in optical systems. So, likewise for a light wave in a medium, this is the picture that we want to keep in mind. An unattenuated propagating wave enters into a medium, the amplitude can decay with an absorption depth 1 over alpha, right. This is an exponential process in the variable z, as well as it essentially undergoes a phase modification by the real part of the refractive index n causes the change or the modification to the phase. So, we looked at nonlinear media, where again light polarizes the medium, and we asked the question about what if the motion isn't sinusoidal, and realized that if the response of the medium and the which is linked to the motion of the electrons or the displacement of the electron cloud or deformation, whatever you like to call it, then if this isn't sinusoidal, there is some nonlinearity in the response for whatever reason, then we immediately start seeing the harmonics of the primary radiation in the process of light interacting with matter. Okay. So, the medium becomes this nonlinearity becomes the nonlinear polarization of the medium. In linear optics, all of linear optics is captured in this relation, P is epsilon naught chi 1 E, where chi in this case is written like a scalar, but it could be a tensor or a dyad. Now, when we consider nonlinear optics, we need to write everything down as a perturbative series in E. P is a function of E, and we have everything else to be a perturbative Taylor expanded series in E, right. So, if we look at the second term, that is the E square term, obviously by writing the real field script E to be equal to exponent I omega t plus E star, that is the star of the complex conjugate of the amplitude, exponent plus exponent minus I omega t, that is a piece and its complex conjugate. Then squaring this gives us immediately the second harmonic as well as a DC term. Okay. So, now the polarization term happens to be and should be viewed as a source. The source term for polarization can oscillate at the initial driving frequency omega or twice omega or thrice omega, or in the case that there are couple of different waves of different frequencies present, you could have the second harmonic, and you could also have the sum or the difference frequencies of the two participating waves present through this equation, as well as have this rectification term where there is a static DC field inside the medium which is produced. Okay. So, these are all important aspects of second order processes. So, second harmonic generation can also be viewed as the absorption of two photons by a single atomic center, or it could even be a particle. As long as there is sufficient coherence, we can observe second harmonic emission. This can be viewed as the simultaneous absorption of two photons by the medium onto the dashed lines here represent so called virtual states. An upward two photon transition is made, where by two photon transition we mean the simultaneous absorption of two instead of just one photons by an atomic center, right. And the system essentially lives very briefly, if at all, in this at this virtual state, and it decays emitting just a single photon of 2 omega. The absorption coefficient, 2 photon absorption coefficient of a medium is measured in Goppert-Meyers. One Goppert-Meyer is 10 to the minus 50 centimeter to the 4 s 4 seconds per photon. It is a bit of a complicated expression, but it is of course true. Now, okay, in the previous lecture we discussed the concept of photon density. So, let us take it forward from here as to what we mean by photon density and concepts thereof, right. So, the probability of detecting a photon at a position r within an area dA is proportional to the intensity of the beam. Okay, intensity of the beam is I of r. For a beam of light, as we saw yesterday, the intensity for a beam of light, which you can consider to be something like a laser beam with a Gaussian frequency profile, that this beam has an intensity defined at every point along the transverse coordinate, which is r, right. Just take an axis like that. We essentially would have a beam with an amplitude sort of varying like that, if you wish, and at every point r we are wherever we have an interest in determining the intensity, or rather the points are here. So, R1 we can have another point R2 here, and so on and so forth. We can calculate the intensity as we might want it to be the case. Okay. So, this essentially now gives us the a correlation between intensity and detection probability of a photon at any given point in space. If I consider a disk of area dA, then these two quantities, the probability of detecting the photon at with on a disk of area dA centered about a location r is proportional to the intensity. Okay. So, that is typically how we view this. So, we discussed the notion of intensity in some detail yesterday and how it applies to photoabsorptive phenomena, right. So, we spoke a lot about second harmonic generation in the last couple of lectures. So, let us see here the first example of the demonstration of second harmonic generation, which today is a very commonplace phenomenon, okay, demonstrated by Peter Franken. Note here that this paper was published in 1961. Okay. Now, essentially in this case, the point to note is the related fact that the laser itself that the optical laser, not the maser, was invented in about 1955. So, within a few years people applied this, like scientists applied this to generate the second harmonic, okay, using a ruby laser in the red part of the frequency spectrum. This was the first, remember this is the first laser to be demonstrated, the ruby laser, right, in a quartz crystal. Okay. So, they generated, see the ruby lasers, primary lasers wavelength was 694 nanometers or 694.3 nanometers or 6943 angstroms. Then the second harmonic of that is in the blue, it is a, right, it is blue, violet blue region of the spectrum, 347 nanometers. Okay. So, this is 2 omega is half 2 omega is half the wavelength, isn't it? So, how did Franken and co-workers determine the that they had generated the second harmonic? Okay. So, they used a prism, a simple prism over here in the experiment to separate these two frequencies, and this part of the experiment is a prism spectrograph, a fairly crude one you might say, but this technology is quite similar even today. So, if you are setting up a high order harmonic generation process, the template is the same. So, you start with a laser, then you introduce a focusing element. Even today for a lot of purposes we do use a lens for focusing, and then you have the nonlinear medium. In the case of high harmonic generation, this could either be a medium made of a solid, a condensed phase target, or it could also be a gas. If it is a gas or a liquid, we will not see second harmonic, we will not see even harmonics, we will come to that. But the rest of this experiment is basically a spectrometer, right. So, you would then need a spectrometer to and disperse the radiation, collect the harmonics which say appear in blue, actually it is more like a violet blue. So, let us take that. So, here depending on the shape of your beam, whatever it might be, you should have seen a violet beam, but typically the intensity of the harmonics tends to be a small fraction of the incident beam. So, let us put a small dot over there, whereas the incident beam itself was in the red. So, this is what one expects to see in the experiment, and nowadays with modern lasers this is a fairly straightforward thing to set up, and like we do it in our lab too. Maybe we can maybe demo this for the live student class here. Okay. So, that is the process of second harmonic generation, which was published in 61 in this iconic paper in Physical Review Letters. It is more than 60 years ago, but there is a little anecdote to this. The actual published result, the first demonstration of the second harmonic generation data, this is the data as published in the paper, right. So, where did we say the primary beam was? The primary beam had a wavelength of about 700 nanometer or 7000 angstroms. So, this is the scale in angstroms, or angstrom divided by 100, that is the scale. You can see here this is 8000 angstroms, 7500, 7000, 6500, 6000, 5500, and so on and so forth. That is the spectrograph. Okay. So, one expects to see the second harmonic at 3472 angstroms, which is somewhere here where the arrow is marked at this position on the scale. Do you see? I mean, this experiment, by the way, I should mention this. The experiment uses, or used, not uses, used a photographic plate. It is the 1960s. Remember, the detector is a photographic plate. So, the entire thing, or let us do it like that, this entire thing here is a photographic plate, right. That is the data recording medium. Now, in a photographic plate, you just have in these plates a monochrome black to white and shades of gray indicating intensity, like good old photographic films, right. So, here at this location, one expected to see something, a patch like what is seen over here. This is omega, but do you see a 2 omega here? Do you see anything in this dotted line? Let me erase that region. Do you see anything over here? I am trying to draw your attention from all sides just to show that, oh no, at this place there seems to be absolutely nothing, okay, in the published result, which was published in a very respectable journal. Okay. Now, the point being that this is an artifact of history. A proper reproduction of the data should have introduced something like maybe a tiny spot here, however tiny it may be, right. But the spot is very weak because the efficiency of harmonic generation can, depending on your system, be even just a few percent of omega. Okay. Efficiency of second harmonic generation could be a few percent of omega when you try this for the first time, and your medium's nonlinearity, that is chi 2 value, is very modest. Okay. It is not, there are media with very appreciable chi 2s. We will come to, we will look at how to generate good substantially strong second harmonic. But then we see absolutely nothing. So, what is the proof that second harmonic was generated at all in this experiment? It just so happened that there was a very tiny dot here, and remember that these were the days of the photographic plate. Now, we show a very cleaned up image here. There were probably little dots all over this plate or whatever. I am just imagining this to be a real scenario, because there is signal and there is noise. Even in the most expensive of CCD cameras, cooled and whatever, you do have dark counts, right? We do have dark counts. So, amidst that sort of a thing, in those times, copy editors, their role was to clean up a bit of, if you might say so, unintended specs and whatever, or we may use the word junk for it, or dirt, whatever adjective we like to use. He thought, while cleaning up the mess, so to say, he also cleaned out the signal. So, an overzealous editor really cleaned out the actual data point, right. So, if we were to really look at this on such a scale, so you have like a huge histogram for lambda of the fundamental, and perhaps have maybe even this is probably exaggerated. We should maybe introduce a break in the scale while plotting something like this, so that we plot these two guys on, say, two independent axes for the signal, right. So, this is signal of 2 omega, this is signal of omega. So, if this was plotted on a scale like that, on the same vertical scale, the second harmonic, one can imagine, would be something like that. Okay. This is not yet a very advanced application of second harmonics. Today, a modern second harmonic generation with good crystals and everything done nicely can give you 30 to 40%, maybe even in excess of 40% of second harmonic, depending on how well we do that. Okay, so historically, what the editor did was, he said, oh, okay, this is all, there is some noise in the signal in throughout this plate. So, we just, he wiped out, maybe she, the editor wiped out everything and clean this out, yeah, so that everything looks clean, and finally you saw only the, what we would call the pump. This is the lambda is the pump. Of course, this is on the same scale, lambda over 2, this is 2 omega, this is omega. So, here there should have been a signal. Okay, I am drawing histograms because just to emphasize the fact that, so I mean data is histogrammatic in some sense, right, we plot the histogram. Okay, so that is the first demonstration, quite dramatic, that indeed one can see nonlinear effects. Now, as when this was done, right, soon after, in a few years, of course, the inventors of the laser got a Nobel Prize for this. So, Nobel for the laser, right. So, was given to Charlie Towns and two Russian physicists, Prof and Bazov, but this opened up a whole field of nonlinear spectroscopy, which I alluded to yesterday, that now we have new sources of, for doing spectroscopy of various kinds, exploiting nonlinear effects and spectroscopy, and a prize for, a Nobel Prize for this was awarded to Nicholas, I think there is just one O, Blumbergen. I do not quite recall the years, but very close by. Okay. So, this is this was as dramatic an event. So, I am essentially mentioning the Nobel Prizes to highlight the fact that the 2023 3 Nobel Prize in Physics which went to people doing high order harmonic generation, or the pioneers of high order harmonic generation received a Nobel Prize. The pioneers of low order harmonic generation, if you wish, the fathers of the laser, as well as I would rather compare it more with the prize to Bloembergen and the prize, this current Nobel Prize, I would put them on similar scales of comparison to say that this opened up a whole new area. So, we may now say that we are in the second or third revolution, or maybe one can count more, of following the invention of the laser and going into nonlinear processes and physics and technology enabled by that, right. So, this is not the first time that the laser plus harmonic generation has yielded a Nobel Prize. It has already happened in the past, but as we say, science, in science you see, you look at the horizon and the limits by standing on the shoulder of giants. So, these are the giants on whose shoulder, on which the current year's prize was also built up, so to say, right. So, this is how science progresses, a great example in the evolution of humankind's scientific thought, if you wish. Okay.